Hi, this is Al, your probability and statistics instructor again. Okay, let's begin doing some probability theory. The main two topics that I would like to discuss with you in this short video lecture are the following: the concept of probability function, and the second topic would be probability space. Let's begin with the first one, probability function. Before I give you the formal definition of a probability function, I would like to discuss with you an example that will illustrate that you already know a lot about probability functions. Okay, here we go. Example. So consider the following random experiment. Random experiment. Drawing an M&M candy at random from a bag of candies. Okay? If you have a chance, go to your nearest convenience store, get one of these little bags of candy, M&Ms, and you'll see that they come in one of 7 colors. So the outcome that we're going to be paying attention to is that color. Okay, so we have a random experiment. The sample space, since we're going to be paying attention to color, will be one of the 7 colors. One of them is purple, the other one is yellow, red, orange, brown, green, and blue. Okay, so that's a list of all possible outcomes, 7 possibilities. And now these guys from this company have information about the proportions for each of these colors, and they happen to be the following. Those proportions: the proportion of blue candies is 0.2, proportion of yellow is 0.2 as well, proportion of red happens to be 0.2 as well, proportion of orange candies 0.1, proportion of brown also 0.1, proportion of green 0.1. And proportion of blue, guess what? I don't have it. Okay, so that's information that we have. So note that those would be the probabilities of our outcomes. Now, what if we want to answer the following questions? What must be the probability of blue? Second question. What is the probability that you do not draw a brown candy? Last question. What is the probability that the candy you draw is either yellow, orange, or red? Okay, let's answer those questions. And again, this is a simple example, but the purpose of this simple toy example is showing you that you already know a lot about the properties of a probability function. So, solution for the answer for the first question. What must be the probability of drawing a blue candy? Well, we go back to the information that we've got about the other colors. And by the way, here the first one is the probability of purple, right? For some reason I was thinking about blue from the beginning, but anyway. So now let's pay attention to this. We know that, you know, the probability of the sample space, the probability of drawing either of those 7 colors must be 1. You're going to draw one of those colors. So the probability of the sample space is 1. So probability of sample space must be 1. On the other hand, so we already have all the other possibilities. So the probability of blue must be 1 minus the sum of these guys, of not drawing a blue candy. So it must be 0.6 plus 0.3, that's 0.9, so 1 minus that must be 0.1 as well. That would be the probability of drawing a blue candy, right? Let's write it down here. Probability of blue, 1 minus 0.9 equals 0.1. But again, what I want to stress is the idea that we were able to find this number, the probability of blue, as a consequence of this fact that the probability of the sample space equals 1. Okay? Now let's turn our attention to the second question. What is the probability that you do not draw a brown candy? So let's think about this in terms of our fancy notation. Okay? So if we use our fancy notation and we denote brown with, let me see, 1, 2, 3, 4, 5. So let the event brown be denoted by A5. Okay? In that case, the probability of not drawing a brown candy happens to be, using our fancy notation, probability of not brown happens to be the probability of A5 complement, right? Let me fix that here. We want that subscript 5. There we are. That's a probability that we want. Now it makes sense that the probability of not brown would be what? The sum of the other guys. That would be one way of finding it. So it would be 0.2 plus 0.2 plus 0.2 plus 0.1 plus 0.1 plus 0.1 from part A. That would be the probability of not brown, but note that another way of finding this would be 1 minus the probability of the event of interest. Let me be lazy here. Just copy paste. You guys agree that that makes sense? That the probability of A complement for any event A is 1 minus the probability of A. Right? Okay. So in this case, that happens to be 0.9, we said. Right? So 1 minus 0.1 equals 0.9. Excellent. So that's the answer for our second question. Let's try and solve the third question. What is the probability that the candy you draw is either yellow, orange, or red? So we have the individual probabilities, and we are ruling out the possibility of getting a candy that, you know, has two different colors. So it's only one of them. Okay, so let me again use some notation. For yellow, let's use A2. For orange, let's use A4. And then for red, A3. Make sense? So yellow, A2, A3, A4. Make sense? Here we go. Let yellow be A2, A3 will be red, right? And orange will be A4. So using that notation, what we are looking for is the probability of A2 or A3, but or we know is a union. So A2 union A3 union A4. And then what's the probability of yellow or red or orange? What you would do is just add these numbers up, right? The information that we already have here. Yellow plus the probability of yellow plus the probability of red plus the probability of orange. So before we write that down, let me write it in terms of our events and using our fancy notation. So the probability of A2 union A3 union A4 equals the probability of A2 plus probability of A3 plus the probability of A4, right? So the probability of a union equals the sum of probabilities. Make sense? But that's provided that these guys, these events, don't have any sample points in common, right? And if they don't have any sample points in common, we have a fancy term for that. We say that, for instance, in this case, A2 and A3 are mutually exclusive. Same goes for A3 and A4, right? They are mutually exclusive. Well, and then this happens to be just 0.2 plus 0.1 plus 0.2, which equals 0.5. Make sense? Okay. Again, the most important part of this third question is that I wanted you to see this, that it is intuitive that the probability of a union of mutually exclusive events is going to be equal to the sum of their component probabilities. Make sense? Or the events that make up that union. Well, I want you to note something else about this simple example. These 7 colors are all the possible outcomes as far as colors go for this random experiment. Okay? And we don't have any intersections between them, and well, these guys, these events, if we call them, if we refer to them using our fancy notation, A1, A2, A3, A4, A5, A6, and A7, they form a partition of the sample space. There's another term to refer to a partition, a decomposition of the sample space. So, and a partition or decomposition of the sample space has that property that the union gives you the sample space, and the pairwise intersections are disjoint. Okay? Okay. So, just a little note. A1 A2 A3 dot 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 A7 are an example of a decomposition also known as partition of the sample space S. Why? Because AI, the intersection between AI and AJ equals the empty set for I different from J, right? If those indices are different. And let me write it down with that shorthand notation here. The union if we start at 1 and we end it at 7, we only have 7 possible colors of the AKs, which are the events that represent each different color, give you the entire sample space. Okay? Okay. So now we are prepared to discuss the definition of a probability function. Okay, here we go. Formal definition of probability function. Definition. Of probability function. So, suppose S is a sample space associated with an experiment. So, suppose S is a sample space associated with an experiment. To every event A in S, we assign a number. We're going to denote that number with P of A. Okay, that's the probability of the event A. And that number will be called the probability of A. But that number that we're going to be assigning to the event A must satisfy a few conditions, properties, so that condition number 1, the number that we assign must be a number between 0 and 1. Condition number 2, probability of the sample space must be equal to 1. Condition number 3, so if we have a sequence of pairwise and pairwise mutually exclusive events in the sample space, right, then the probability of the union must be the sum of probabilities. Here we go. If A1, A1 A2 so on, form a sequence of pairwise mutually exclusive events in S, and probability of A1, oh, sorry, A1, let me copy and paste this guy. Union A2 union dot dot dot, right? We have infinitely many of them, is going to be equal to the summation, to the sum of the corresponding probabilities. Probability of A sub k, k goes from 1 up to infinity. Make sense? Good. Okay, so that's the formal definition of probability. As you can see from that simple toy example about the colors of M&Ms, you already knew a lot about that, right? All of those numbers satisfy this condition. They are numbers between 0 and 1. The probability of the sample space was 1, and then to find, for instance, the probability of a union, what we did is just do a sum of the individual probabilities. Individual meaning the probability for each of those outcomes, of those events that make up for the union. Make sense? Finally, after providing the formal definition of a probability function, finally we are prepared to talk about the concept of a probability space. So, in another video we talked about definition of a random experiment. In another video we also talked about and introduced the sample space, and in a previous video we also, that was kind of a long one, we introduced the important concept of a Borel field, beta. And now we have this new concept of a probability function. Well, those three guys, the sample space, the Borel field, and the probability function, those three ingredients are going to help us define a probability space associated with a random experiment. Okay, so let me just write that down. A probability space consists of three fundamental ingredients. Let me call them that. And they are: 1, sample space, S, or remember we also use the capital Greek O omega to refer to the sample space. B, Borel field. We used beta to refer to a Borel field. C, probability function P. These three quantities constitute a probability space associated with the random experiment of interest. And notation, it is denoted by S, beta, and P. Okay? So, summary of what we just did. Summary. Today we talked about two important concepts. The concept of a probability function P, which is just a function that goes from the sample space to the interval 0, 1. We're assigning a number in 0, 1 to each of those events in the sample space. And note that it was important to introduce the concept before of a Borel field, because like in our toy example, we weren't interested just in a simple outcome. Hey, what's the probability of blue? No. On the third question, what's the probability of drawing a yellow or red or brown, right? So that's a combination of simple events, right? So if you go back to what we said about Borel fields, right? Back then what we said is that one of the properties of a Borel field is that it contains the unions of the events in the Borel field, actually the infinite unions. So that's why we had to talk about that guy, because the Borel field is going to give us this wide variety of combinations of events, basically all the events that we could be interested in. Okay, so the other concept that we talked about here, the important concept, was the probability space. Which is the three components that we need to provide a mathematical description of a random experiment. And a probability space has three components, three ingredients: S, the sample space; beta, the sigma field or Borel field associated to S, to that particular sample space; and P, a function, a probability function that satisfies those three properties that we talked about, that the numbers that we're going to be assigning to any event are going to be numbers between 0 and 1, the probability of the sample space equals 1, and if we have decomposition or partition, right, of the of an event, then all we have to do to find the probability of a union is doing or computing the sum of probabilities of the components. Make sense? Okay, So just let me here point that out, that we also mentioned along the way the concept of a partition or decomposition of S. Make sense? Okay, so that's it for now. See you next time. Please take care and keep working hard. Bye.